Okay, so today we're going to pick up where we left off last lecture. Um, so you may remember last time we started talking about EVs and batteries. This was after last week doing kind of a eat your vegetables week of learning about math and kind of how to code and simulate DERs. So this week we are talking about, we're actually digging into some DERs. So on Tuesday we started talking about batteries and EVs. Today we will finish that off and then move on to modeling the thermal dynamics of buildings. So how temperatures within buildings evolve as a function of weather and what we're doing with heating and cooling equipment and things like that. So yeah, last time we talked about stationary batteries, how we model them, how we find the parameters. We talked about 6 different parameters that go into the kind of stationary battery model. And then we talked about EVs as basically batteries that can move around and how to get data and stuff for those models. And then we talked about 3 different policies. We kind of ended up on Tuesday for how we charge electric vehicles. And I should say there are many, many different ways that electric vehicles can be charged. We talked about sort of 3 simple policies on Tuesday. As we move on through the semester, eventually we will learn about how to use computers to do optimization to come up with something like an optimal EV charging profile. And then, there are various notions of what that can mean, optimal for who, optimal for one vehicle or for a whole fleet of vehicles, things like that. So we'll get into this in much more detail as the semester goes on. But for now, to kind of, again, like the kind of vibe with this class is that we don't go super duper deep into any one particular technology, but I kind of want to give you enough to sort of get your hands dirty and be a little bit dangerous when you apply, these tools to sort of various systems. So that's the spirit of these EV charging policies. We already went through the math, so I won't go through it again. I just want to remind you what the 3 policies are, because you will write code to basically simulate these policies in your homework. And then I will go through a couple of graphs in a minute here that show what the outputs of some of these charging policies look like. So the first one is very simple. It's basically, just plug something in and then it charges full blast until it's full or until you unplug it. The second policy basically said similar thing, but you specify sort of a minimum acceptable energy, and you don't charge unless the battery is below that energy. So you might say 40%, 50%, something like that. And so we talked about how to code that. And then the third policy, basically similar to the second policy, but rather than charging full blast, you specify a deadline. I want 80% full battery by 8 a.m. tomorrow, and then you charge steadily, sort of constant rate, in order to basically place the final energy at that specified level. Okay, so then we'll show numerical examples, and then I'll flip over to show a MATLAB version of this code, slightly different from the Python version, but not too different. So this is basically the input data for the simulations. So we have an electric vehicle that has a 80 kilowatt hour battery, pretty big, but by no means the biggest that you can find in an EV today. We're doing a 7-day simulation. So in this graph here, we have the time axis going from 0 to, I guess, 170 or something like that, which is 7 days in hours. And then on the vertical axis here, we have the power that we're discharging for driving. So we talked about this thing we called alpha, the energy intensity of driving, which would be like an energy per distance, kilowatt hour per kilometer, something like that. And we talked about how that's related to the distance that you drive, but also a function of the vehicle, the speed that you're driving, all sorts of things like that. So what's shown here is the energy or the power that is discharged basically as we're driving around. So here, the short trips, like these little guys, I assume that they are done at 40 kilometers per hour, which I think is about 25 miles an hour. And the longer trips are done at 90, which I think is around 55 or 60, somewhere in there. So these are the longer trips. They're done at higher speed and also typically for longer distance. And so the area under these kind of tall curves is typically a little bit bigger than the area under the short trips. And then the shaded periods here represent basically when the electric vehicle is plugged in and capable of charging. So you'll notice that all of the spikes related to driving, that all of those fall during the unshaded periods. So we're not simultaneously charging and driving around. You need a really long extension cord for that, I guess. Okay, so that is the input data. These are the car trips that are driven over the course of a week. And this is what the first policy looks like. So again, on the x-axis, we have the same thing, time in units of hours that runs for the 1 week time span. On the top plot here, we have the stored energy in the battery, so basically the state of the battery. And you can see that basically each time we drive, there's a dip down in the stored energy. And then each time we charge, sorry, I guess I'm not showing the driving energy here, but so for example, during this period, there are a bunch of short trips, each of which results in kind of a step down in the stored energy during those periods. And then basically at the start of each night, whether we need it or not, basically we just charge full blast until the battery again reaches its full state. So here there were some longer trips. We charge for a while on the first night and bring the battery all the way up to full. Makes sense? I feel like this one's fairly simple, but any questions about this one? Okay. And then policy number 2 basically says, okay, do something similar to policy 1, but only do it if you are below a certain minimum energy. And here I've set that energy X min at 40 kilowatt hours, which is half of the full capacity, the 80 kilowatt hours. So you can see, even though we're driving and even though we're plugged in on some nights, we're only at, say, 75% energy right here. We're not below that 50% threshold, so we do not charge. But then there's a long trip and we get down to maybe 15-20% energy here. And so that night when we plug in, we charge full blast for a while, actually almost the whole night, in order to bring the energy back up to its full capacity. And then similar thing, we slowly deplete over the course of a few days. Eventually we drop down below half charge again and boom, back up to full. Yes, question.
Yeah, at least in the round, trying to work through the initialization of the variable y, the charging status, was set to where it resets each time to not charging. So if we're trying to get not to just ride the minimum battery level, we might have to put in a reinitialization in the loop to be equal to the charging status of the last step.
Okay, I'm going to try to paraphrase your question for the video, but first of all, are you working in MATLAB or Python? MATLAB. Okay, and then is this in code that you wrote, or is it a chunk of code that we gave you? Okay. That you may have modified. Okay, so I guess to paraphrase the question here for policy number 2, if you reinitialize this Y thing, basically the indicator of are you in charging mode or not, if you reinitialize that at every time step, then you said you found a behavior where basically it would charge, but it would stop charging at the minimum.
And without doing this, so in your chunk of code, you initialized it to where all the charging is set to not charge at the beginning of the step. So unless you reinitialize.
Yeah. So right, there is logic in here that basically reinitializes this Y depending on the conditions. And so you should implement the logic that's kind of in these 2 bullet points. So here the variable Z, you may remember, is an indicator of whether the thing is plugged in or not. So this first line here says if the car is not plugged in, or if you have reached, you've filled up the battery, you reach the max capacity, then turn off charging mode, basically. And then the next bullet point here says, well, if you are plugged in and if you are below the minimum threshold, then turn on charging mode. So yeah, so these are updates. So that vector Y in the code that I gave you is initialized at all zeros, I believe. But it shouldn't stay all zeros. Like it should get updated based on what you were doing in the previous time step. Does it make sense? Okay. So if it's not, you're not getting the expected behavior, then my guess is that you've implemented something.
Why I implemented something so that
okay, I see.
Like if you leave the Y initialization as you left it, then you ride the bottom curve.
Okay.
But you have to put in another piece in the loop and say, hey, Y, if it's not off, then Y should be the last Y that was in the last step.
Yes, right. So that's this initialization that you start this thing at whatever it was in the previous time step. Yeah. Okay. So anyway, there may be mistakes. I have the code in front of me and I'll run it and we'll see what it looks like. But yeah, you need to be a little bit careful about how you update these variables in your code for sure. Okay, for now, I'm going to move on to show the third policy here. So this one is similar to the second policy, but rather than charging full blast, basically we try to spread the charging out over the whole night. So here we're driving, we deplete the battery, eventually we drop below the minimum threshold. Okay, now we charge. And this actually looks just like policy number 2 because we pretty much have to charge full blast in order to fill the battery in one night. So it's not quite the same, but it's pretty close. But over here, this charging period will look quite different. So here we charge full blast for half the night, and here we charge at about half power, but for the whole night. So you can imagine if you are a power grid operator, maybe the distribution grid operator, something like that, where you have to size things like wires and transformers to accommodate peak power demand. You can imagine that this power profile, where we're sort of slow and steady charging, might be a lot more friendly to your infrastructure than this one, where we do a big spike of high power and then turn off. It also can have issues for like what the voltage is within the grid and things like that. Okay, so one of the points of feedback I got in discussion with students last week was basically it would be nice in these homework assignments if I could walk through the code that I give you guys a little bit more so you have a sense for kind of what's happening overall and not just in like the chunks of code that you guys are filling in. So I will briefly do that here. So this is, I guess, my version of the code. It doesn't look exactly like the version that I put on GitHub. I think that version has like kind of a preamble section up here, which defines a bunch of stuff for the graphs, basically. Those are set as defaults on my computer. I put them in what's called the startup.m file, which basically it runs every time you turn MATLAB on. So there's some reconfiguration of things that I like to do to kind of customize how my plots look and stuff like that. But anyway, I give you that stuff in separate chunks of code so that hopefully your plots will look similar to how my plots look. And then, so I'm using what's called cell mode here, or I don't know if that's still the term that MATLAB uses, but basically each of these chunks of code that you break up with the two comment characters, you can then collapse and expand a cell. So it makes your code a little bit more compartmentalized and sometimes easier to read. So the first chunk here basically just specifies the input data. So this is the timing. We started at time 0, and D, this is the number of days, and then this defines the simulation time span. Here we have the parameters for the electric vehicle. So these are the 6 things that show up in the EV model. So we have the self-dissipation time constant, and then from that and the time step, we get the parameter A that shows up in the discrete time dynamics equation. And then we have the efficiencies and the charging capacities, the energy capacities, and so on. And this X min is what you use, I guess, in policies 2 and 3 to define the minimum kind of acceptable amount of stored energy. And alpha here is the energy intensity of driving. This thing could be more complicated. It could be dependent on the speed. It could be dependent on the weather and things like that. But here, kind of for simplicity, it's just a constant. And then this is the chemical driving power is generated from a function. And I don't think this is one that you guys need to fill in. But all this basically does is it takes the time span and the energy intensity of driving, and then it returns the chemical charging power that is dissipated from driving. So in this function, I build distances and times when those distances are driven, and then I use an equation to basically back out how much energy that uses. And then here, this is that indicator variable Z that basically says, is the car plugged in or not? So I think all that stuff is the same in your version of the code. And then this is just drawing, this chunk of code here just draws the first graph that I drew, that I showed in the presentation today. Now, these are randomly generated. So in your code, this may look a little bit different than what it looks like in the slides that I showed just now. But that's okay. The general, basically, the logic for how the policies work should be similar. Okay. So yeah, this is just a plot. And then policy number 1. So I believe now in the assignment, you're asked to basically fill in this function here. And this just implements the logic that I put up. And yeah, so this one should be fairly simple, but we have the outputs of this function are the profiles. So over time, over the 170 hours or whatever it is, of the stored energy and of the electric charging power. And I call those X1 and P1 because they correspond to policy 1. We'll have different versions of them for the policies 2 and 3. And then this takes the initial state, how much energy is in the battery, that indicator variable Z, and then the dissipated power for driving, and then basically the 6 parameters of the battery. And then this thing just draws the plots, basically. So I guess we can see what that looks like in case you're curious. You can also just like dig into the code. I've tried to be careful about putting comments on everything. Every variable, has units and a description. And then this tells you what all the inputs and the dimensions and so forth are. But basically this just draws one subplot in a 2x1 matrix, right? So this is a column of plots, and this last argument says plot in the first row of that. And then, yeah, so we do, this is called a stair step graph, and then there's an area graph for the other one. All right, and then similar thing, basically for policy 2 and policy 3, these code chunks look just like they do for policy 1. And then we define a couple of other parameters. So this is the deadline. How many hours ahead do we require the charge X star to be met? And then what do we define? And here I'm just saying X star, the desired charge at the end of the period, is just equal to the max. So we're saying we want 100% charge after 6 hours. All right, so if we run policy 1, what does that look like with this different randomly generated data? About like this. If we define policy 2, okay, now we are only charging once we drop below the minimum here. And then policy 3, let's see what that looks like with this input data. Quite similar in this case to policy 2, but again, kind of spreading out the charging slow and steady over the day. So questions about this? Oh, okay, just moved your hand. Okay, gotta hold very still or else I'll call on you. Okay, so that wraps up the sort of battery and EV material, at least for now. And you have everything that you need to work on the homework assignment that is due next week, Wednesday, just before midnight. And now we're going to transition to talking about buildings. But any questions about anything really on the EV or battery material before we dig into buildings? And again, folks online, please feel free to just speak up. I can't see the chat right now, but just go ahead and interrupt me if you have a question, please. Okay. So we're going to do 2 lectures on thermal modeling of buildings. And so today we'll do kind of a simpler lecture, I guess, and then we'll talk in somewhat more detail about this stuff next week on Tuesday. So why 2 lectures on this when we spent 1 lecture on both EVs and batteries? Part of this is because I have done a lot of work historically in buildings. I think they're really interesting. It's more, kind of in my wheelhouse. Yeah, I mean, yeah, it's my class. I could do what I want, I guess. But also, and we'll go into a little bit of the motivation here. Also, buildings are a pretty large part of the electric power sector, and have some inherent flexibility built into them, so they can be used for various purposes on kind of operating the power grid more efficiently, more reliably, and so on. So. Also, buildings are kind of complicated. I guess any of these topics are kind of complicated. I just know more about the complexity of buildings because I've worked more on them myself. Okay, so just a little bit of background and some reminders. I think I've already shown some of these plots, but why do we care about buildings? And here I'm showing over time from 1950 out through, I guess, last year, or maybe 2 ago, the electricity sector, basically the supply and demand of electricity in the US specifically. So here, this is broken out by economic sector where the electricity is used. So this is the industrial sector. Industrial sector is at the bottom of the stack here. So this is manufacturing, chemical processing, all sorts of things like that, mining, machining, and so on. This is commercial buildings is the middle wedge here. So office buildings, hospitals, educational facilities, things like that. And then the green bar here is residential, apartments, houses, condos. And then transportation is almost invisible here, but there's a tiny yellow sliver that represents electricity used for things like public transit systems, where you might have electrified trains in a city like New York, for example. We have some electric rail that goes between cities, but very, very little of it in the US, although in other countries, there's much more of that. And then let's see, direct use wedge. Oh, right, there is a little bit of electric vehicles. So, all the all the cars and trucks and SUVs and stuff that people are driving, but it's currently still very small, even though growth rates in that sector are large. And then at the top of the stack here is what's called direct use. So this would be, for example, if an industrial facility has a natural gas plant on site, but all the electricity it generates is used at that facility for powering things internally. Or this would be stuff like rooftop solar sitting on an office building or a house, something like that. Okay, so the main point here is that if you look at the building sector, so this is a combination of the residential and the industrial sector, this uses around 3/4 of electricity. So about 3/4 of the grid is driven by buildings. And this is energy. And if we look at peak demand, which again, I mentioned this a little while ago, but you know, the size of the infrastructure we have to build on the grid is really more directly related to the peak power flow through the grid than it is to the overall energy use over time. So things like, you know, how fat the wires need to be, how big the transformers and substations need to be, all that stuff is dependent on the peak. And so if you look at what drives peak electricity demand, in most places in the US, the peaks happen on the hottest afternoons of the year, driven primarily by air conditioning in buildings. So buildings matter a lot for energy, for cost. They also matter a lot for peak and for the sizing of infrastructure. Slightly different view here, but similar materials. So here we are looking within the building sector. So this is combined commercial and residential buildings. And we're looking at a breakout of the blue bars are how energy is used within buildings. And then the orange bars are how electricity used specifically. So the blue includes electricity, but it also includes, for example, burning natural gas for space heating or water heating. And then here are the end uses, and the y-axis here is the percent of the total, either percent total energy or percent total electricity. So space heating today, about 38% is used, sorry, of all the energy used in residential commercial buildings is for space heating, only 9% of the electricity. So this basically tells us that most of the heating in buildings today comes from burning fossil fuels. Water heating, okay, cooling, so this is air conditioning. Ventilation, this is largely, you know, big fans in commercial buildings to provide fresh air in rooms like this. Refrigeration, and then this is everything else. So you can see that half of the electricity basically comes from heating, space and water, cooling space, and then ventilation and refrigeration. And then that's about 2/3 of the energy. So 1 minus the 32 would be 68%, I guess. And this is today, right? And then we've talked about kind of what the likely, well, I don't know if it's likely or not, but what one future, one scenario that we could look at for decarbonizing the building sector and the economy more broadly involves shifting a lot of fossil fuel combustion over to electricity. So if you imagine taking all of this energy that's currently used for space heating, for water heating from fossil fuels, and shifting it over to electricity, then these shares would go up a lot. The electricity shares. All right, so that's a little bit about why we might care about the thermal modeling of buildings. And then I guess this will be probably kind of review material for some people who have taken a class like heat transfer, but for people who have not, I just want to sketch out a little bit of the complexity that is involved in kind of detailed physical modeling of buildings. So here I'm drawing kind of like the simplest building you can imagine. This is a one-dimensional thing. Over here we have a window, and then over here we have a wall. And the orange here is shortwave radiation, basically sunlight. So you can see that some of that is reflected from the window, some of it is transmitted through, it hits the wall, and then it scatters. And you could imagine tracing each of these rays, you know, that bounce off of the wall and the reflection, and they could, you know, bounce around, and there would be this iterative process of transmission and reflection and so forth. So even just keeping track of what's happening with all that sunlight could be quite challenging, even in this super simple geometry. The wiggly waves here represent thermal radiation. So when we were talking about solar energy and the model of Earth's climate, we talked about how everything that is at above absolute zero temperature is radiating energy through thermal radiation, what's called black body radiation. So this wall might be warm, it might be exchanging thermal radiation with this colder window, say if it's cold outside. This window also would be radiating this way, but there would be kind of a net transfer of energy from the warmer surface to the colder surface that it sees. And then maybe the window is warmer than the rest of the world, so there might be a net transfer of energy via radiation from the window out to the surroundings. These kind of curvy things represent convection. So if the surface is warm and cold air from outside comes close to it, that air is going to warm up, and then thermal buoyancy effects will cause it to kind of move upward. And then you get these convection cells that represent heat transfer kind of out to the ambient air. You might have a similar thing happening inside. There can be internal heat sources, so body heat, lights, electronics, things like that, which might emit energy both through convection with the indoor air, but also through thermal radiation. And then inside of this wall, there's also a conductive effect. So maybe the inside is warm and the outside is cold. So you'd have a temperature gradient through this wall. And that temperature gradient basically is modeled through a partial differential equation called the heat equation. That's kind of what this looks like up here. And there would also be complicated fluid mechanic effects happening inside as well. So all the convection and things like that. So modeling all of that detailed physics and in a complicated building geometry, high dimensional problem, many parameters, nonlinear partial differential equations governing the dynamics. So even just writing down all those equations and finding the right input data for them is a very complicated process. And then how you solve those equations numerically is also can be a real challenge. So there are software packages that basically do that process that I described. Probably the most commonly used one today is called Energy Plus. This is an open source software system that's developed by the US Department of Energy. There's another one that does a lot of what Energy Plus can do, has some other bells and whistles, often related to things like solar energy and thermal storage and so forth. But this is called Transys. It stands for Transient System Simulation. This one you would buy. There are sort of graphical front ends for Energy Plus that you can also buy that kind of streamline running it. And then in the last roughly 10 years, a language called Modelica, which has, again, an open source language, but there are kind of closed graphic user interfaces tools for that that are developed. And there's a buildings library specifically for Modelica. So from some folks here in Herrick Laboratories in the ME department might have friends who use Modelica for simulation purposes or might use it yourselves. So all these tools they're quite cool. What happens under the hood is actually, I think, mathematically and physically really interesting. They're also, Energy Plus and Transys in particular are very broad general purpose tools. So whatever you may be interested in, there's probably a module that somebody somewhere has built that does it. So if you're interested in dispersion of virus particles, as people sneeze inside of a room, how that, the virus stuff migrates around a room, for example, for COVID transmission. You can probably find an Energy Plus or a Transys module that can help you simulate that stuff. We are not going to be doing things like that in this class. So the downsides of some of these tools, I guess I've kind of mentioned it, is that it's really hard to specify all the input data that you need in order to run the simulations. If you specify inaccurate input data, the outputs of your simulation might also be inaccurate or meaningless. Because they have these high dimensional nonlinear partial differential equations, the numerical solution of those equations can be challenging, and that often means slow in terms of compute time. And then this is varying, and other people might have different takes on this, but they can be difficult to integrate with other software packages. So for example, we will learn in this class about how to do numerical optimization, and trying to plug in something like Energy Plus with an optimization tool can be done, but it is not super straightforward. Okay, so in this class, we're going to focus on simpler models that I think both A, give a little bit more intuition physically for how this stuff works, and B, can be plugged in with like optimization packages and things of that nature a little bit more easily. Okay, so the basics of the model structure that we will use is called a thermal circuit. So we'll start by talking about first order thermal circuits. And actually on next week's lecture on Tuesday, we'll talk about second order and higher order thermal circuits. And I'll mention what that means in just a sec here. So we'll talk about basically the structure of the equations, similar to how we started talking about batteries, right? We wrote down a fairly simple differential equation, and then we will talk about how to get the parameters that go into those models. And we'll talk about a couple different approaches here. Okay, so a thermal circuit is what it sounds like. It's like an electrical circuit, but rather than having charge flowing around, we have heat flowing around. And there's a clear and direct analogy between DC circuits and electrical circuits and thermal circuits. So the idea here in this analogy is that temperature is sort of the driving potential in the same way that voltage is the driving potential in an electrical circuit. So there's an analogy between temperature and voltage. The thing that flows around is charge, right? So current is the flow of charge. And we will talk about heat or the flow of heat in thermal circuits. And then there's a direct analog between resistors on the thermal, on the electrical side, and capacitors as well. So a resistor basically is something that impedes the flow of current or the flow of heat. And then a capacitor is something where charge or heat can accumulate. Okay, so the very simplest version of a thermal circuit is also probably the one that is most useful for modeling things. This is called the 1R, 1C circuit. And here the numbers just represent the number of resistors and the number of capacitors in the circuit. So here, T again represents temperature. So you can imagine for a building model that this would represent the indoor air temperature, basically the thing that's measured on that wall thermostat. And then theta here would be the outdoor, well, it would be a boundary temperature. Very often it's the outdoor air temperature, but you can imagine if we're thinking about an underground bunker or something like that, it might be the ground surrounding the bunker. R, this is a thermal resistance. It has units of temperature, dimension of temperature divided by power. And then C is the thermal capacitance. So again, this is basically the energy storing or the heat storing element in the circuit. And then these things here are basically current sources or heat sources. And so QC represents thermal power. So we would have units of kilowatts, but kilowatts of thermal energy rather than electrical energy. And this is basically what's coming from the heating or cooling equipment. So, what's coming out of that radiator in the back of the room. And then QE, it is not at all a sunny day today, but if it was, QE would basically represent the heat that's coming into the building from sunlight. But also it would be the heat that's coming off of energy dissipation from that projector, from our body heat and things like that. Okay, so it's probably been a minute since you wrote down, use Ohm's law and Kirchhoff's circuit laws and things like that to get the equations for a circuit. So we'll just walk through quickly how that works in this 1R, 1C context. So Ohm's law basically says that V is IR or delta V, the change in voltage over a resistor is equal to that divided by the resistance is equal to the current flow. So we essentially are saying that the current, so the heat transfer, the rate of heat transfer across this thermal resistor is equal to the temperature difference that drives that current flow divided by the resistance here. So that is Ohm's law. The equation for the charge accumulation or the heat accumulation in a capacitor is basically C times the derivative of the temperature, or in an electrical circuit, it would be C times the derivative of the voltage measured here. And then there Kirchhoff's circuit laws, there's a voltage law and there's a current law. And we will use the current law here. And this basically is just conservation of charge. So it just says that if you pick a node here, the current flowing into that node has to be equal to, or the sum of all the currents flowing in is equal to the sum of all the currents flowing out. So we're not building up charge at this point in the circuit. So if we apply the current law at this node here, we get the current inflow, which is just the sum of these QC and QE terms. And then the current outflow is the current over this resistor, which we get from Ohm's law, plus the current that's going into this capacitor. And that's the same as the current that's building up on the capacitor. So we plug in the capacitor charge accumulation formula down here. And we will rearrange this and get basically the governing differential equation. So if you move the C, so I guess move this term over to the left-hand side, divide through everywhere by C, factor out an R, we get this equation here. So 1 over RC times this term here where we have temperatures, and then we have R times those thermal power source terms. So this is a first order linear ordinary differential equation. It has more terms in it than the one that we wrote down for a battery, but it actually has really similar structure to the battery equation. So we have time derivative. Over here, we have a state variable. This is kind of like the energy, but it's the temperature in the thermal circuit example. And then we have some other stuff. So all these kind of additive terms in the equation basically play the same role that the charging or discharging power plays in a battery equation. And then I'm just going to jump right to kind of the answer for this. But if you apply the equations that we wrote down last week for how to get the discrete time version of a continuous time ODE, if you apply all those equations to this guy up here, then we get this formula for the dynamics of the indoor temperature. So the new temperature is just A times the old temperature plus 1 minus A times the thermal resistance times, oh, I see. Okay. So times this thing here, which is basically, this is like something we can control. So this is maybe the energy coming out of a heating or cooling system. And then W here is basically everything that we can't control. So this is both the boundary temperature theta, outdoor air temperature, something like that. And then it's also kind of the uncontrolled heat that we're getting from sunlight, from body heat, and so forth. And I believe that there is a homework problem this week that basically is just showing how this works. So putting in the steps to get this equation. And the parameter A here is, so you may remember for batteries, A was equal to negative delta T divided by tau, where tau was the self-dissipation time constant, and typically is on the order of like 1,000 hours for a lithium-ion battery. So in this equation for buildings, the product RC, so let's see, R has units of degrees per kilowatt, and C has units of kilowatt hours per degree. So if you multiply those together, everything cancels except for hours. So the product RC has units of time and actually defines what's called the time constant of the dynamics of the indoor air temperature. Okay, so that is a 1R, 1C circuit. So now we can get progressively more complicated and add in different numbers of capacitors and resistors. The order of the equation is determined by the number of capacitors in the equation. So I mentioned we're talking only about first order thermal circuits today. So they will only ever have one C, one thermal capacitance term. But actually you can get large numbers of R's and get still sort of complicated looking models. Okay. So in this circuit, we have, again, maybe think of this as the indoor temperature. This Tm here, we could represent, or we could use that to represent sort of the average temperature of the thermal mass in a building. So that could be like all this stuff. It could be the concrete and the floors and the walls. You could imagine, so that temperature does change over time. So you could imagine having a 2C model where that mass temperature has a capacitance associated with it, a Cm, in the same way that the air temperature has a capacitance associated with it. And if we use that model, then we'd be modeling the energy storage capacity of all that thermally massive stuff. But here we're basically assuming that the treating this Tm here is kind of a boundary temperature in the same way that we were for the outdoor temperature. And then we have a thermal resistance between the indoor temperature and the thermal mass. And we have another resistance between the indoor temperature and the outdoor temperature here. So it turns out that you can rewrite a 2R1C circuit as an equivalent 1R1C circuit. So this is probably something that you did like in E&M at some point in earlier classes. But this is the governing equation. It turns out you can write this down from, again, doing the same process using Ohm's law and Kirchhoff's current law to write down the governing equation. And if you do a little bit of algebra, you can show, so this thing has a T in it over here, a T in it over here. You can show that if you define an equivalent thermal resistance R and an equivalent boundary temperature theta in this particular way, then you get that these two equations are in fact the same. So I'm not going to go through all of those steps, but if you want to kind of fill in the blanks, it's a fun exercise. Yes.
So if you go back to the circuit really quick,
Mhm.
I'm just wondering, there's kind of like an open circuit there along like your wires, I guess. Is there a reason like you have that little break like below T out and TM or?
Oh, yeah, what am I drawing here in this sort of open circuit representation? So these are drawn as batteries, basically, or voltage sources. So here, like in an electrical circuit, this would be ground.
Yeah.
And then this would be a battery that basically raises to a certain a certain voltage here. So this could be 5 volts or something. And then this is another battery, again, ground here, and then this would raise to a different voltage, potentially 10 volts or something like that.
So in the thermal circuit, what does it represent?
In the thermal circuit, what does this battery represent?
Yeah.
Nothing really. Nothing.
Okay.
It has no particular physical representation. It's just we're just saying that these things are basically boundary temperatures in the same way that a battery provides like a boundary voltage for this circuit. That's a good question. Thank you. Yes, Grace.
Like, if we look at it from right to left, does that make sense to do it that way?
Yeah, so the question is, if we think of this as a circuit, like an electrical circuit, could we look at these things as sort of a filter, like a low pass filter? And yeah, I mean, if you look at this differential equation, if you squint a little bit, this essentially ends up being the equation of a low pass filter. And the time constant basically determines what that cutoff frequency is that you're filtering out noise above that. So yeah, these things do have direct analogies to filters. They don't end up being super useful, at least in work that I've done previously, but if it helps you build intuition for like what the dynamics look like, then yeah, for sure. And then Grant, did you have a question too?
I was just gonna ask if it's like correct or acceptable to think of those batteries as like the generation from the sun or the generation from inside the earth. It's like sources and just a way to think of those, or it could be incorrect.
Yeah. So the question is, would it be correct? So if we look at this battery, for example, to think of this as, kind of the action of the sun, of, maintaining, if ground here is absolute zero, for example, maintaining the temperature of the earth at, I don't know, 280 or 290 Kelvin. Yeah, I think if that helps you kind of understand what's going on in the circuit, then yeah, I think you can think of it that way. It's reasonable. Yep. Okay, so that was a 2R1C circuit, and then it gives a little bit more modeling flexibility, basically. So in this circuit, you could imagine maybe you do a 1R1C circuit where you use only the outdoor temperature and the indoor temperature, and maybe it doesn't end up fitting the data or the dynamics that you observe very well. So you could imagine maybe going to a 2R1C circuit and saying, oh, there must be some other temperature that we're exchanging heat with that kind of slows down or speeds up the dynamics. So you can imagine wanting a little bit more modeling flexibility in order to match the data that you see experimentally a little bit better. And then you can go one step further or n steps further if you still don't get the modeling flexibility that you're looking for. So here I've shown kind of a generic circuit. Again, maybe this is indoor temperature. This might be the temperature of an adjacent room or hallway. It could be the temperature of the hallway out there. And then we could have a bunch of other boundary temperatures related to the upstairs temperature, the downstairs temperature, the temperature of that room, the outdoor temperature. So you can imagine specifying all of those, attaching a resistance to each of them, and then writing down a model for the thermodynamics of the whole room. Yes?
Super quick, so in this model and then the previous ones, most of your resistors are, in parallel. Can you have them in series in a model, or like why do we model it in this way?
So the question is, all these resistors are in parallel. Could we model series resistances? Yes, absolutely, we could model series resistances. So, and that's actually often done in kind of reduced order modeling of, for example, conduction through walls. So you might say, have like one temperature node at the outside surface of a wall, another or at the inside surface, another at the outside surface, and you might put a couple in the middle. And like, so maybe there's like a plywood layer and then an insulation layer or something like that. So you might basically at the interface of each layer, you might put a new node in there. Yeah. And you could again use, all the rules that you use, Ohm's law and so forth for modeling to come up with the equations for that as well. Yes. Yeah, good question. Other questions about this?
Similarly, can we, if we were to basically consolidate and reduce out to one resistor, can we use the same laws to calculate one single resistance to evaluate the circuit?
can we calculate the resistances, like get a number for R1 and for Rn and so forth? Yes. And so sometimes that can be done directly by thinking about the thermal properties of the materials. Like, so for example, if we were thinking about conduction through that wall, you can think about, okay, what is it made out of? Cinder block. Okay, what is the conductivity of cinder block? And you can go from there to getting at least an estimate of R. It would have to do with the thickness of the wall as well, things like that. That's one way to do it. Another way to do it would be to look at data. So look at the measurements coming off of the wall thermostats and things like that. And then try to use that to sort of back out what the parameters of the model must be. So that's sometimes called inverse modeling. Yeah, and we'll talk a little bit about at least something about how to fit these models to data as well. Yeah. I think there was another hand. Yes.
So, could you give like an example of like why we would model in parallel versus in series? Like, series makes sense being like the layers of insulation, but in this case, would this be like a room inside of the building?
Yeah, so I guess the question for folks online is, could I mention again why we would want to do series versus parallel resistances? And then in particular, like if this is say a room, what would these temperatures and resistances represent physically? Yeah, so we could think of that, maybe this is the indoor temperature in this room. So that's roughly what the wall thermostat is measuring. And then maybe T1 is the temperature out in the hallway there. So this R1 would represent basically the resistance or the thermal conductivity of the cinder block that makes up that wall. But also it might have to do with air sort of leaking under the door over there. And in particular, if I prop that door open, you could imagine that this resistance here would change. It would decrease because the rooms would become more tightly coupled, if that makes sense. And then, there are a bunch of other resistances and temperatures, boundary temperatures, and we could think of those as being, again, other adjacent zones. So one could be the outdoor temperature, another could be the temperature in the room upstairs or downstairs over there. Yeah, totally. And then why we might do a series resistance. So suppose that there were multiple materials inside of that wall. There might be like brick, and then there might be an air gap, and then there might be some insulation. I don't know, we usually don't insulate interior walls, but just bear with me. So you might want basically to assign different resistances to each of those different materials, and then have kind of intermediate temperature nodes, basically that would represent that wall. Those are good questions. Thank you. Okay. So again, I won't go through all the gory details, but if you do the usual circuit laws here, you can write down a governing differential equation for this. Because there's only one C, there's only one energy storage element, so there's only one equation. And it has the dt by dt here, so a derivative of the indoor temperature with respect to time in the same way that the other circuits did. And then here, this is a summation with n terms in it. And n can be arbitrarily large. It could be 10, it could be 100, it could be 1,000 in a really complex model. So the key feature of this NR1C circuit is that it only has this one capacitance in it. So then we get only one governing equation. But you can write this down, and then you can kind of play the same game that we played with the 2R1C circuit, which is defining an equivalent boundary temperature, which ends up being a weighted average of all of the boundary temperatures T1 through Tn. And the weights are basically defined by all the thermal resistances. And again, you can kind of convince yourself mathematically that this is true. Actually don't remember, but there may be a homework problem on this week's assignment on this. I think I may have cut it from the assignment. I'm not really sure. But anyway, it's fairly straightforward algebra to get from the previous equation to this one. And so this again has the same form of the 1R1C circuit that we started. So it's actually, there's a fair amount of flexibility that's actually built in to that 1R1C model, because it has the capability of basically modeling these equivalent boundary temperatures. Okay, so that's all in terms of model structure. And then here we will talk a little bit about the model parameters, how we find numerical values of them. So I'm going to go through the same kind of process that we did for batteries. We basically write down all the different types of parameters that show up in the model, and then we'll talk about how to find numerical values for each of those. So there's really only three types of parameter that show up in this model. There's the thermal capacitance, there's the thermal resistance. These are both positive scalars. And then there is the what we call the exogenous thermal power, or you could call it a disturbance term. Some people call it the internal gains. And this is a time series. So to simulate a model, we'd only need to define one number for R and one number for C. But if we're simulating for a week at hourly time resolution, we'd have to come up with like 170 numbers to represent this entire signal or time series. So we'll talk about each of these in turn, starting, I guess, from the simple one, which is the thermal capacitance. So the thermal capacitance here can be modeled as the density times Cp, which is the specific heat at constant pressure of air, times the volume of air enclosed in the room. And I'm just giving you numerical values for those things here. And the volume you can write for a rectangular room, typically you write it as the floor area times the height of the room. Okay, so this is basically the thermal capacitance of the enclosed volume of air. But in this 1R, 1C model, if you actually look at data and you try to fit it to data for real buildings, often we find that in fact, the dynamics, if we just use this, end up being like way too fast. Temperatures change way too quickly. And the reason for that physically, there are a couple of them. But one of them is that there's a lot of stuff in this room that is basically at the same temperature as what we measure in the wall thermostat there, and that it's pretty tightly coupled thermally to the indoor air. So for example, all the like aluminum or whatever in these lights is there's air flowing over it constantly. It's thermally very light, so likely it's kind of at about the same temperature as the air. And then if you looked at, I don't know, you like drilled in and took a core sample or something of this hunk of laminate and plastic here, and whatever's in there, plywood, you probably find that the surface temperature here is about the same as the air temperature. In fact, there's a boundary condition that says that the temperature here has to be basically the same as the air temperature. And then as you got further and further inside, the temperature might be different. So anyway, if you take into account the fact that all of that stuff is tightly coupled with the air, then we end up with basically more thermal mass associated with that thermal capacitance that we're modeling. So for that reason, if you look at data, often you increase the C that you would get just by doing the calculation on the air only, increase it by about an order of magnitude to account for all that tightly coupled stuff. And then the model typically will fit real data much more accurately. Another reason for this is that, so actually the temperature of the air in this room is not a single number. It's really a three-dimensional scalar field. So depending on the X, Y, and Z coordinate that you choose in the room, you would have a different temperature measurement. In particular, due to thermal buoyancy, it'd be hot near the ceiling and cold near the floor, probably. So actually, when we put in heat from radiators or from an air conditioner, there are mixing effects, and it takes some time for the air to mix, and then for the temperature change to actually show up at that wall thermostat. So there are delays associated with that physical mixing process, and those are another reason why a slower model, basically a model with more thermal mass in it, tends to fit the data better. Okay, so if we run the numbers here, we plug in all the coefficients for a 200 square meter, about 2,000 square foot house, kind of a typical home size in the US, with ceiling heights of about 3 meters. Okay, so typical ceiling heights in the US. You might get a value of this thermal capacitance of kind of around 2 to 3, somewhere in units of kilowatt hours of thermal energy per degree Celsius. Okay, so that was the easy part. The thermal resistance, R, is much harder to get an accurate value for. And so I'm going to present a couple of different ways that you could go about getting a value for that R. Okay, so we'll begin by basically finding a way to come up with this resistance as a function of weather data and some energy usage data. So you can imagine looking at an energy bill or measuring, say, the thermal energy that is supplied to this room by the radiators in the back there. Okay, and then so if we start by making kind of a steady state assumption. So let's assume that there's some temperature set point. That would be like the number that we put into the wall thermostat, say 72 Fahrenheit. And let's assume that even though the temperature in this room is somewhat dynamic, let's assume that it's pretty much constant and it's pretty much at the desired value. So this is basically assuming that the control system for the thermostat and the heater is basically working well. And then let's also assume that the energy we're getting from these kind of exogenous sources, sunlight, body heat, all that stuff, is roughly constant. Okay, so in that case, the steady state assumption basically zeroes out this time derivative. And then we have our governing equation, the right-hand side here. We can solve this basically with a 0 on the left-hand side. We can solve for the energy that's basically delivered to the room or to the building by mechanical equipment. So this ends up just being a delta T over R, and then we subtract off this constant for the other thermal power. Okay, so then let's suppose, and this is kind of a leap of intuition, but let's just imagine that we can guess some number, some delta T, basically, call it little, this is a lowercase Greek delta, such that if the temperature between the inside and the outside is equal to that number, then we don't need any heating and we don't need any cooling. So the mechanical equipment would turn off, basically. So it's like maybe it's 70 Fahrenheit inside, and then that's maybe the temperature that you choose for heating in your apartment or your house. You can kind of imagine that you could guess, well, what's the temperature outside at which the heat's basically not going to run? So let's, I don't know, think of a number in your head and then we'll say it out loud. So suppose you like it to be 70 inside, how cold would it have to be outside before the heat would turn on? Let's take like 10 seconds and then we'll just shout out our numbers. Who has thought of a number? All right, well, so what's your guess?
Like 65.
65 outside? Okay, so 70 inside, 65 outside.
Warm it up a little, and then the air comes in a little bit.
Okay, what was your guess? So you think the heat would run in your house if it was 72 degrees outside, even if you only want it 70 inside? That's okay. Sorry, I don't want to like be too skeptical. Let's just go around the room. So 72, what other guesses do we have? Jennifer? 66, 65, okay.
Right.
Yeah, exactly.
I thought of it
Yep, great. 40 to 50, okay, a little more extreme. Any other guesses? Low 60s? Yeah, okay. So the answer to this, there is no answer, right? It's going to really depend on the building, and it's going to depend on how well insulated it is and all sorts of other stuff. But the point is that like you can get a plausible guess for this by just kind of thumb in the wind and taking a swing at it. Okay, so in the event that you can come up with a guess at this, and we have this kind of steady state assumption, so we get this governing equation, then this QC is equal to 0 when the delta T, the T hat minus theta, the outdoor temperature, is equal to this lowercase delta. So in that case, the equation simplifies. Yeah, and so we get basically that the heat supply, QC, is just equal to, now this numerator is just equal to our lowercase delta divided by R, and then we subtract off whatever this is. And so that's all equal to 0. So we solve that and find that there's a relationship between the Q hat, the delta, and the R here. And I promise there's a reason why we're doing this, but it'll take a slide or two to get there. It also gives a simplified expression for the heat that we supply, the energy we supply to the house. So if you take this equation and we basically, let's see, solve this for delta here, delta. Wait, what am I doing? Oh, I see. Okay, so we take this expression for QE and we plug it in up here. So we substitute in the delta divided by R in for this term in the QC equation. Then we get basically only temperature terms in the numerator and a denominator that is only the resistance R. And then we define a new variable here, theta H, which is called the heating balance outdoor temperature. And that's just equal to the indoor temperature set point minus delta. So this theta H is basically the number that you guys shouted out, the number at which there's no heating needed in the house. Okay, so now, really soon, I promise we're gonna get to some answer of how we define R. So define the cumulative heat demand that we provide to the house, integrated over some time period. So maybe you have an energy bill for a month. So this could be the monthly heating demand. And this could be for a commercial building, it could be for a home. I'm just saying house to kind of to be concrete. And then using our expression that we got in the last slide, that the heat supply is approximately equal to this balance temperature, theta H, which is a constant, minus our outdoor temperature, all divided by R, the resistance. Then we can take this expression for the total heat. By the way, the max function here, I've mentioned it before, but this basically just takes it's a function of two variables that gives you back the larger of those two variables. So max of X and Y gives you back whichever is bigger between X and Y. So this basically says that if Q is negative, then that means there's actually cooling demand from the building, and so there's no heat needed. So if you're measuring the fuel input to a furnace, you would not get any measurements during those periods when QC is negative. But when QC is positive, then we just integrate it directly in order to get the heat supply to that. Okay. So we just take this expression, plug it in for QC here. That's all we've done in this integral term. And then we make a definition, which is that this thing I've denoted with a capital Greek theta H, is an integral of a temperature. So it has units of temperature times time. So this is the number of what are called heating degree hours, or change units, heating degree days at this heating balance outdoor temperature, little theta H. So that thing is just the integral of theta H minus the outdoor temperature. Take the max of all of that, integrate it with respect to time. Yes?
What did HBOT stand for? Sorry.
HBOT was from the last slide, heating balance outdoor temperature. So heating meaning not cooling, right? We're thinking about winter, and then balance, really, it's sort of the outdoor temperature at which the heating demand is zero. So, okay. Okay, so now we are almost there. So if you imagine that we have an energy bill where we have E, the fuel input, measured to, say, a furnace or a heat pump or some other heating system, that is just going to be equal to the heat that's delivered divided by the efficiency. So if we have a conversion efficiency from, say, natural gas to heat of 80%, then E here would be bigger by a factor of 1 over 0.8. It would be bigger than the heat that's actually supplied. The other 20% of the energy content from the fuel would go basically up a smokestack. Okay, so if we put all of this together, we have an expression for H here. H is equal to the number of heating degree hours divided by R. So we solve this for R, we get R is equal to theta over H. And then we plug in from this equation that H is equal to the efficiency times the fuel input measurement, E. Okay, so this is one way that you can look at data, kind of coarse data that is available for most buildings, because we typically measure energy so we can pay our utilities for it. This is one way that you can take information about the outdoor temperature and about the energy usage and the equipment efficiency, and from that we get an estimate of this thermal resistance. So it's not too hard to find databases because it's just directly calculated from weather information of the heating degree, what are called heating degree days. So this would be in units of degrees Celsius or degrees Fahrenheit times days rather than times hours, which is what that data thing is that I showed. You can find that for both heating and also for cooling. So here are maps of the US. This is actually cooling on the left-hand side here, with a base temperature, that balance outdoor temperature of 65 Fahrenheit. Some buildings will be lower than that. Often, I think the houses that I've worked with might be kind of in the 50s or something, but often for whatever reason, we choose 65 when sort of showing this data graphically. But it's kind of what you would expect. So there's a lot more cooling needed in the Southeast, especially in Florida, Texas, et cetera, in the Southwest, especially, Arizona, Southern California. And then as you get further and further north, into Montana, Wisconsin, sorry, not New Mexico, Minnesota, that the demand for cooling ends up being close to zero. So essentially no air conditioning needed in Maine. Now these maps will change as the climate changes, right, as the world gets hotter. And then this is the heating degree days at that same balanced temperature of 65 Fahrenheit. And again, it's kind of what you might expect. So along the Rocky Mountains in the Mountain West, high elevation, a lot of heat needed. In the north, Minnesota, Wisconsin, Maine, et cetera, there's a lot of heat needed. Yes.
Two questions. I guess, remember we're calculating. We agreed is if we didn't go through the other method, would we just take the number of days? Like, so if I wanted to see on the heating degree day from today, I would take the temperature of today minus 60 or minus 65 or plus the other way around, the difference between day and 65
Mhm.
times 1 day. And then if I do it for the last 2 days, then take those temperatures and average. Like, and I get a certain number of degrees per day.
Yeah, so the question for folks online is basically like, how would we calculate heating degree days if we had specified that balanced temperature, say 65 Fahrenheit? If we knew the temperature today, the temperature yesterday, and so forth. Yeah, so if you had a data set, like a spreadsheet that was like day or the date, and then the average outdoor temperature for that day. I think what you would do is you would basically take that average, subtract it from 65, the balanced temperature. So suppose today's average temperature was like 35 Fahrenheit. So we would take 65, subtract 35, that would give us 30. And that would enter, we multiply it by 1 day, and that would be 35 heating degree days from today. And then maybe yesterday was a little bit colder, maybe it was 30 average. So we would get, I guess, sorry, I did the math wrong there. 30 degree days from today, and then 35 from yesterday because it was a little colder. And then you just progress through your data set, your whole spreadsheet, doing that calculation and add it all up, and you would get, this is order of 1,000 cooling degree days for Indiana. And for heating Indiana, it's probably an order of 6,000 or something like that, added up over the entire year.
And the other question was, this is a very macro scale, very, very average. So is the way that we get from Indiana, the average energy expenditure or resistance across Indiana to the average resistance in my house, is that coming from the input of our energy bill that you were talking about earlier?
Yeah.
Okay.
Yeah, so it is interesting, right? So you could do this at various spatial scales. So really what I'm thinking about here is like, imagine, you go home and pick up your Duke Energy, natural gas bill. You would say, how many therms or whatever of natural gas did I use last month? And then maybe convert it to kilowatt hours and then multiply by a typical efficiency for a furnace. And that would give you the denominator here.
Last month.
Yeah, and that you can download, like if you just Google Indiana heating degree days, there'll be some place you can probably download that. Or you could get actual weather data, hourly weather data or daily weather data, and then you could do the calculation yourself. But you're right that we could also do this at a different spatial scale. So you could look at, for example, all of the natural gas that comes into the state of Indiana, and you could assume some portion of it is used for space heating in buildings. And then that would give you an E, and then you could assume kind of a representative efficiency, I don't know, 80% or something like that. And then that basically would give you the denominator, and you could again use the heating degree days, maybe averaged over the state of Indiana rather than for any one weather station. And this would give you an estimate of kind of the overall thermal resistance of the building stock in Indiana. So that can be useful when you're doing like big picture modeling of energy systems across a state or across a country. You probably wouldn't use this method directly. You'd probably use something a little more sophisticated, but this can provide a good sanity check on your data. Yeah, good questions. So we have about 5 minutes left. We summarize this, and then maybe we'll stop and take any remaining questions that you guys have, and then pick up with another method to estimate this R parameter on next week, Tuesday. I'll just do the summary slide, and then we'll do questions real quick. So, okay, so this method that we just described involving heating degree days. You could also do it for air conditioning. It would involve cooling degree days, but the equations look super duper similar. So the process basically goes, okay, first you think about the building that you're working on, and you say, okay, roughly what is the indoor temperature? and that could just be the thermostat measurement from the wall. And then we estimate this little delta, the indoor-outdoor temperature difference, or just an outdoor temperature at which no heating is needed. So this might be, I think our test house off campus, it's about 8 degrees Celsius, which is roughly, I guess, 15-ish degrees Fahrenheit. So for our house, if it was 70 inside, we would say probably below about 55. That's when the heat would turn on. So if it's 58 out, we probably don't need too much heat inside the house. But this number will vary, and it'll be small for badly insulated houses or drafty, leaky houses, and it'll be bigger for better insulated type homes. Okay, and then we define this thing, theta H, which we call the heating balance outdoor temperature, as just the indoor temperature minus that delta. We download the heating degree day or heating degree hour data, and this is a link. And I think there's a quick calculation on this week's, sorry, not this week's homework, it'll be next week's homework, where you will use this link, download some data, and do some of these calculations yourself. And then we assume you have access to an energy bill, something like that, and you can back out basically what the energy used for heating was over the period. It could be a month, could be a winter. And then you get an estimate of the heater efficiency. This could come, for example, from looking at the nameplate on a furnace, and then pulling up manufacturer specs. You could also just think about like, how old is this furnace? Sometimes appliances will have like an Energy Star label on them that will tell you, this is a good or a bad appliance. And based on that, you might come up with an estimate. So once you have all that data, you plug it into this formula with a unit conversion. Typically, the weather data will show up in units of heating degree days. And then the other units that we specified, kilowatts and kilowatt hours, require this unit conversion. But anyway, at the end of the day, we come up with an estimate of R, the thermal resistance. So now we have C, which might be kind of order 2 to 3, something like that for a typical size US home. And then we have R, which might be on the order of kind of 2 to 5, somewhere in that range, in units of degrees per kilowatt, for, again, a similar size home. And I'll talk a little bit more about the numbers and a second way that you might calculate this thing, R. And then that gives you kind of 2 ways to come at the same number, which would give you, if they agree reasonably well, it would build confidence that you have a reasonably accurate estimate of R. But we'll talk about that on Tuesday. So any questions?
If you go back like 2 slides, I think,
One more?
to the, yeah, right there, I think. So at some point, yeah, you define E as H over eta, and then in the equation for R, you used eta E in the denominator. Is that reason you didn't use H instead? Or
Yeah, the reason we want to replace H is because the thing that's measured, like on a utility bill, would be typically the input to the heater,
okay,
like say the natural gas input or the propane input. And typically, yeah, and the output is related to that input through the efficiency. But usually we don't measure like the actual amount of heat that's supplied to a house. We just measure the fuel that goes into the heater.
okay.
And then the equation just came from this thing up here, and just replacing H by eta E. Yep, good question. So we're pretty much at time, but any other questions? Yes?
Heat resistance.
Mhm.
If you're modeling like that with the outdoor temperature and also thermal mass, it's a separate temperature. If you're taking into consideration the like thermal mass,
Mm.
you just loop it into the capacitor that you have in there, or is it like on separate?
Yeah, so the question is, if we're working with a circuit like this, but we wanted to take into account the fact that the thermal mass, like all the concrete in this room, actually can change temperature and can store energy in that way. How would we incorporate that into this model? Yeah, so the rigorous way to do that would basically be to increase the order of the circuit to second order. So we would have one state that has to do with the temperature of the indoor air, and then we'd basically take out this battery and put in another capacitor, call it CM, and then maybe we would measure or estimate the temperature of that thing, and we'd have to, again, come up with an estimate of what the thermal mass would be. And you could, again, back that out by looking at its volume and density and specific heat, things like that. Yeah, and we will talk about second order thermal circuits next lecture. Yeah, please.
If you have like some building material that's like that,
Mhm.
that's absorbing kind of
Mhm.
right? So then that's that thing.
Yeah.
the thing.
Yeah. This is in electrical circuits, it'd be a current source, I guess. Yeah.
Where does that capacity?
So that is another excellent question. And we would actually redraw the sort of wiring in the circuit diagram. But the question is about what if your thermal mass was like getting direct sunlight and maybe it's painted black or something. So it's absorbing a lot of that sunlight and really warming up. So the temperature change of the thermal mass would not be driven primarily by the air temperature getting hot and then bleeding heat into the mass, but it would just be getting heat directly from the sun. So yeah, then we would want a connection basically from this QE directly into the thermal mass. So you can imagine drawing like another current source that would like just inject right here into the thermal mass. Yeah. I don't think I'll have a diagram like that next lecture, but we'll talk a little bit more about this next lecture. But those are great questions. Yeah. Okay, we're at time. So anybody who wants to take off, please feel free. And then anybody who wants to keep chatting, again, feel free. But I'm going to stop the video here.